right, we're going to talk about Green's theorem, a very, very important theorem in multivariable calculus. Um, this builds up from other theorems that are similar, and it is good to see the other theorems to compare. So we have the fundamental theorem of calculus, which most of us have already seen and we use periodically. If you find the definite integral of the derivative of a function, so there's something special about this function. It has to be the derivative of a function. Um, then we can evaluate the definite integral by plugging in the endpoints, the two endpoints in the interval, um, and then subtracting into the antiderivative of this function. So that's why this has f prime, because that is a derivative, and consequently the antiderivative would be just f by itself. And all it takes is one antiderivative. There's multiple antiderivatives, by the way. Yeah, so we could have, for instance, if you start out with x, the antiderivative with respect to x would be x squared over 2 plus 5, for instance. And then you would have b squared over 2 plus 5 minus the quantity a squared over 2 plus 5. So the two 5s cancel off. Now you have to have a specific number, such as 5 or 7 or pi, when you add a constant. If you just have a constant, a generic constant, then the constants don't cancel off because it's a generic constant. And when we add two generic constants, we end up with another generic constant. And when we subtract generic constants, same principle. So we have to have specific numbers. We usually just use 0. But nonetheless, it is important to point out that there are multiple ways of finding this f, or using this f. As I said before, you can add 5. It won't matter because here when we subtract the 5 again, we'll end up with 0. Then we saw in previous videos the fundamental theorem for line integrals. So what is the requirement here? And that's why I was making a big deal about this and the multiplicity, the things we can have here. So the requirement here is that we have to have a gradient, just like here we have to have a derivative, so that, yeah. And then we find, typically, they don't tell us what the antiderivative is. We usually have to figure this out. Similarly here, oftentimes we do not know, if we want to use the fundamental theorem of line integrals, what the antiderivative, the antigradient is. We have to figure that out. And again, we plug in the endpoint, we plug in the beginning, and then we subtract. Notice the difference here. We have a straight segment, while here we could have some kind of curve in space. And that's it. Oh, no. There's one more thing. Just as with up here, we could have multiple antiderivatives. We just have to be consistent, grab one, and then use the same one in those two. Same thing here. We can have multiple antigradients. All you have to do is add a constant, and you have a different one. So make sure you use the same one for the two of them. That's why we typically use 0 for the constant, so that we don't have to worry about that. Okay, so now we got Green's theorem, which is what this video is about. So Green's theorem says, all right, if you have the double integral, is there a way where we can look at the boundaries and integrate over the boundaries instead of the whole surface? See, not necessarily integrate, but use the boundary and not the entire region over which we are integrating. See here, in this case, we're not, we're only using the boundary. So the boundary of a segment is just the front end and the back end of the segment. That's it. There's only 2 points. It's like a road. How can you block a road? We'll just block one end, block the other end, and that's it. Those are the 2 boundaries. And typically you cannot get off the road. Pretend there is a bridge. Yeah, so you cannot jump off the bridge. And there's only an end and the beginning. Those are the 2 boundaries. Here, this is similar. There is pretend this is a road for which you cannot really get off the road. So there's only two boundaries, at the end and at the beginning, and that's it. Now here we have a region which we're going to label D, capital D. So that is the region we're integrating over. Can we use the boundary? Now mind, the boundary here would be the edge of the region. Here, the edge of the region is just those 2 points, just those 2 points. Pretend you have a tube again, and what do you need to plug the tube so that if there is a liquid inside and nothing spills out, all you have to do is put your finger in this, put your finger in this, and that's it. Then you got boundaries. Here, well, there's no finger to put anywhere. You cannot just plug a tube. This is a whole region. So you have to go all the way around to look at the boundary. So the boundary is relative. Here, boundary is 2 points. And here, the boundary is the whole entire edge of this region. All right. So can we use that? And the answer is yes. Now, just as up here, we have to have a requirement. We have to have an antiderivative in order to use the fundamental theorem of calculus. We have to be able to obtain a gradient. This function may not seem, and that function may not seem that, I guess we have always assumed that we can always find antiderivatives, but that is not necessarily the case. And it is certainly not the case that all functions are conservative, as we have seen in previous videos. So there is something special about this function before we can apply this fundamental theorem of line integrals. Well, similarly, here we have to have something special about this function so that we can use Green's theorem. What is special is that there's got to be two functions, P and Q, so that when you do the partial of Q with respect to X, partial of P with respect to Y, and then subtract in this fashion, you're gonna end up with this function, yeah, that we are double integrating. So I guess we can label this as F. Yeah, this is the output is one-dimensional, and down here, we split up this integral, double integral, into a single integral with two parts to it. This could be a little misleading because somebody may think, oh, so we're doing 1 and 2, so that is 1 and 2. That's not true. Those are completely different things. This is a line integral, and that is a double integral over a region versus a line integral over a path. So this is a path, which is the boundary. So this F has to come from, I think it would be easier to, in my opinion, even though books typically write just those two, this equal to that as Green's theorem. In my personal opinion, I think it's better to rewrite it as P comma Q dr, because dx, dy form dr. And we're assuming that r is a vector, so that makes sense. And we're doing the dot product. The dot product, you multiply P dx and Q dy. And if we label this as F, then we really have a regular line integral of a vector field over a path. So that's really what's going on. I think it's more, in my opinion, useful to think of it this way, where F is equal to PQ, and where this little f is the partial of Q with respect to X, partial of P with respect to Y. This is a little difficult to remember sometimes. The way I remember is because I think of F, F as the determinant where the first row is partial, just partial, not of anything, just the operator by itself. I want to erase this. There. So operator with respect to X, operator, partial operator with respect to Y, and then just P and Q. this is not part of the equation. I'm just showing you how I remember this part. So, but that's me. So we apply the partial with respect to x to q on the determinant, and then we subtract the partial with respect to y on p. So multiplying those two is not really multiplying, is applying this operator on p and applying this operator on q. Yep. So that does it. So that is Green's theorem. Make sure you know it. It is very, very handy. Now, once you find in Calc 1, in using the fundamental theorem of calculus, the antiderivative, then this is really, really easy. Plug in, you're done. Once you find the antigradient for this line integral, this is really easy. Just plug in, you're done. By the way, this kind of integral is the same as this integral. It's very interesting. So you can kind of step down a little bit. If everything works well, you could actually go down. Yeah. Anyway, you could, I suppose. Anyway, so I lost track of my thought here for a moment. Oh, yes. So this part is easier. This part is typically easier once we find the antiderivative and the antigradient. Here, it is not necessarily true that this is easier than that. That's not necessarily true. Sometimes this is easier and sometimes that is easier. It depends on where the problem. Each problem is different. Sometimes this is easy, sometimes this is easy. Sometimes one of the two is possible, the other one is almost impossible to do because there is just too much work involved in it. Yeah. So that is the quick introduction. One application of Green's theorem. So let's talk about one quick application. The concept of application is relative because a lot of people think, oh, an application means something concrete, and not necessarily. Oftentimes we have a mathematical idea that is used for another mathematical idea, and we label that as an application. And then that could be used for another mathematical idea. So there's levels of applications. And then until we perhaps eventually get down to an application that actually uses things, actual solid things as opposed to numbers, functions, and so forth. So one application is the area, finding the area of a region. So the area of region D can be thought as the double integral over the region of the number 1, simply the number 1 with respect to the area. If you double integrate 1 with respect to the area, you're going to get the area. So that is one way to get a double integral. Now, Green's theorem says if this double integral of this function has this particular form, then we can instead find the line integral of those two. So the question is, can we write 1 as partial of q, partial of, partial of q with respect to x, partial of p with respect to y, subtract, and get 1? And the answer is yes. So this is really, and the thing is, there's a multiple of ways of doing it. Just like up here, there's multiple antigradients, although those are relatively easy because all you have to do is add a constant and multiple antiderivatives. Here, we're going to have multiple ways to do this. So one way, for instance, is to have the integral of, okay, so dq, we could have 0x. Yeah, because PQ, derivative of Q with respect to X would be 1 minus 0. So this will do. See, I prefer this notation, uh, but you can actually break it up into, so nothing here, and then the integral over the boundary of just X with respect to Y. Because remember, this corresponds to X and that corresponds to Y. So the area of a region D could be found by integrating the line integral over the boundary of just X with respect to Y. Yeah, over the boundary. That is very interesting. Now, this is not unique. This is one way to get 1. How am I getting 1? Well, this is, pretend this is P and this is Q. And Green's theorem says if you do partial of Q with respect to X, if this is Q, that would be 1, minus partial of P with respect to Y, which would be 0, we do get 1. So this is one way to go about it. Another way, so let's put an or, another way to do this could be to do negative Y comma 0. Because Green's theorem says, okay, so this is P and this is Q. So Q would be 0, so nothing here this portion does not contribute anything because we end up with 0 minus partial of P with respect to Y. So that would be negative 1, but we are subtracting because Green's theorem says subtract. So the double negative causes to have a 1, and that's exactly what we wanted. So another way to do this is to have the integral over C of negative Y with respect to X. Isn't that interesting? Because this is not completely symmetric. You would think, oh, X dy, so you should have Y dx. No, 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 no. There's an extra negative involved in this. Yep. Or you can combine the two, and there's probably more of them. So we could do negative Y comma X dr. So that actually would be this and that together. But together means that we actually are going to end up with twice as much. So we have to half it to get the same amount, because just the negative Y will contribute a whole area. Just the X will contribute another whole area. So together we have two of those same areas. So we got to divide by 2 to come back to just 1. So you can do a bunch of different things. So you can have half. I don't know why we would want to do that necessarily, but I suppose somebody could, because I think that, in my opinion, this is more work, because if I am doing this, why should I do this plus another one that is going to give me the same answer anyway? But the point of this equation is to show you that this is somewhat flexible. Negative, I should have put the other way around, but no, it's too late. So negative Y dx, close the bracket. I was copying this plus this. I should have brought down this one first, because typically we do dx dy, not the y dx, same thing. Yep. And by the way, the notation for this is half. There's another way to rewrite this, which is, so let me do it right. Negative y dx plus x dy. So this notation means we actually have two integrals, one with respect to x and one with respect to y, one with respect to x, one with respect to y. So this is a new notation. Again, I don't know why I would want to do that, because this calls for finding this integral, which is that one, and then finding that other integral, which is that one. So if I'm going to get the answer with one of those two, why should I find the two of them? But that's just another way to do it. So that is an application. There's something I neglected to mention. I can just draw a picture here. So we have region D somewhere on the plane, and we want to find the area in particular, but we could find the double integral over D of any function. And the question, and the thing is, instead of doing that, we can just use the boundary, which would be here. Notice that I put an arrow. Using Green's theorems assumes we're using the positive orientation of the curve. So curves have an orientation. Yeah, so positive orientation of curve. Very, very important. So that means that the curve is being drawn in such a way that the region we are integrating over as you go on the curve is on your left. Or the other way to say it is that as you see the region from the top, the curve is being drawn counterclockwise, this direction, not this direction. Excuse me. If you do it the other way, then you're going to end up with a negative of what you're supposed to get. So can we do it the other way? Sure. We're just going to end up with the opposite. Yep. So let's do an example. Example 1. We're going to find area of the ellipse x squared over a squared plus y squared over b squared equals 1. So this is the generic equation of an ellipse that goes from the center. Well, the center is at the origin. It goes out a units on the right and left, and up and down b units. And there it is. And an ellipse is a circle that has been tilted, and that gives you an ellipse. So the question is, what is the area of that ellipse? So we're going to use two methods. Method 1, without Green's theorem. Okay, so that means we're going to find, so the area of the ellipse will be the double integral of 1 with respect to the area over the ellipse. Let's call this d. Yeah, d. And now we got to break this up into iterated integral. So we go from negative a to a of, so that is on the axis. On the y's, we got to solve this equation for y. So solving this equation for y means we got to move this to the other side. No, for y. So x squared over a squared has to move. So we're going to have, and then we got to multiply by b squared. And then after that, we're going to take the square root. So we're going to end up with negative b. We're going to assume that b is positive, and so is a. I should squeeze somewhere in here. A is positive, and so is b. So there is that assumption. So we're going to go from negative b square root of 1 minus x squared, 1 minus x squared over a squared, to positive b square root 1 minus x squared over a squared of 1 dy dx. Okay, now, so that means as x goes across from negative a to a, y can go from the lower of the boundary to the upper of the boundary. We're going to have, if you solve for y, you're going to end up with a plus minus square root. The plus corresponds to the top, the minus corresponds to the bottom. Okay, but then you may be thinking, well, the area done that way is really the area, the ellipse is symmetric. So the area done that way is really just finding, 4 regions that are of the same value, and as far as the area goes. So we could just go from 0 to a instead of negative a to a, and then from 0 to this root, this upper value, and multiply the whole thing by 4. So let's do that. Let's simplify by multiplying by 4. This is an even function regardless of how we go. And yeah, so we can just multiply by 2 twice. One would be because instead of going from negative a to a, we can just go from 0 to a. And instead of going from negative of the boundary on the bottom to the positive of the boundary on the top, we can just go from 0 to the top and then multiply by 2 again. So we got 2 times 2 gives us the 4. The integral from 0 to a, the integral from 0. And one thing I'm going to do, I'm going to write this one as a squared over a squared in the root, a squared over a squared. And then we have a common denominator, which will be a squared, which can be factored out. So the upper limit here is going to be b over a square root of a squared minus x squared. Yep, we're still integrating 1 with respect to y and then with respect to x. That makes things kind of easy because then we have 4 times integral from 0 to a of b over a square root of a squared minus x squared dx. Yeah, because 1 is just going to be, the antiderivative will be y, plug in the top, plug in the bottom, so you just end up with the top. Now, b over a is a constant, so we can factor that out. And I'm thinking, I'm thinking for b over a, okay, I'm thinking this. So the b over a factors out. I was actually going to do a trigonometric substitution before, as I was getting ready for this video. I actually had the work done ahead of time. And I was going to do it. But I'm thinking as we speak, this is just, if you look at this portion, this is just a circle of radius a. If you forget about anything else, if you just have y equals square root of a squared minus x squared, that is a circle, well, the upper half of a circle of radius a. And if we're integrating from 0 to a, we're actually ending up with just a quarter. So let me just show you. If you draw y equals the square root of a squared minus x squared, again, that is the upper half of a circle, not an ellipse anymore. It is an actual circle of radius a, not an ellipse. So it goes up a, to the right a, to the left a, down a. Well, not down because this is just the upper half of this circle. If we integrate from 0 to a, we're just getting a quarter of a circle of radius a. So instead of doing the trigonometric substitution as I was going to do, I'm going to just think, okay, this is a quarter of a circle. The integral from 0 to a of this is just a quarter of a circle of radius a. So a circle of radius a has area pi a squared, pi r squared, but the radius is a. So that is the area of a full circle. But we're just getting a quarter of it because we're integrating the upper half from 0 to a. So the 4's simplify, 1a simplifies. So the final answer is a, b, pi. So the area of a general ellipse, if you want to find this area, all you have to do is multiply a, multiply by b, so that is this rectangle, but then we got to multiply by pi rather, and that gives you the exact area of any ellipse. Now, circles are ellipses just like squares are rectangles. I'm going to repeat that. Circles are ellipses just like squares are rectangles, where if this b is equal to a, then we have a circle. Yeah. So if a is equal to b, we have a circle, and the area would be a squared times pi, which would be the same thing as the radius squared times pi. So this does not contradict what we already know about circles. It enhances. Okay, So we use method 1, which was without Green's theorem. Method 2 is next with Green's theorem. All right. So the area is the double integral over the region of 1 dA. Okay. But we have said earlier that we can write 1 as, well, using Green's theorem as 0x dr, which is the same thing as x dy. So this is the line integral over the boundary of x, what did I say, x dy. dy. Now we need one thing though. We need to know how to draw or how to represent the boundary parametrically. So we got an ellipse. This should be fairly short. Anyway, we got an ellipse, A, B. It is, if we didn't know this, now we're going to learn it. It is well known that the parametric function that draws this ellipse in starting here and going around is A cosine t, comma, B sine t. So very much like a circle, except that we have in a circle a fixed radius. It would be the same for both. For the ellipse, we start with A, and then we go to B, back to A on the negative, down to B on the negative, and then back to, as we go around, back to A. So this is going from, the T would be going from, oh, we don't need that side. I meant to put a 0 on the other side. So we go from 0 to 2 pi, and that draws this boundary all the way around. So this is well known. If you didn't know that, please get to know it. So ellipse, the boundary. Okay. Okay. Now, this first coordinate, of course, is what we would label as x, and this is what we would label as y. So we really have the integral from 0 to 2 pi, now that we established that we got to go all the way around to get the whole boundary. X, where's the x? Oh, x is a cosine t, a cosine t, that's x, dy. This is y, so dy would be b cosine t, b cosine t dt. So mind that those two make up dy, and this is x. So x dy. X, this is y, not dy. To get dy, find the derivative with respect to t, which would be cosine of t, times dt. Okay, so we really have a b integral, simple integral, of from 0 to 2 pi of the cosine squared of t dt. Okay. Yeah, there's an important thing I need to mention, but I'll come back and mention it in a moment. Let's finish this up. So this is really, let me do one step over here. A, B, integral from 0 to 2 pi. And we know we have to use a trigonometric identity, 1 plus cosine of 2t over 2 dt. Okay, so cosine of 2t is going to double the frequency. We're going from 0 to 2 pi, so we're going to have 2 full cycles of cosine. Every time you get a full cycle of sine or cosine and we're integrating, we're going to end up with 0. And if we divide by 2, we're still going to end up with 0. So we're really just integrating. So the cosine of 2t in this integral contributes 0 to it. So we're really just integrating 1/2. And the integral of 1/2 is, well, 1/2 t, but then we got to plug in 2 pi and 0. So we have AB times 1/2, the 1/2 times 2 pi. So the 2 simplify, and sure enough, we end up with AB pi, which is the same answer we had in the previous page when we did not use Green's theorem. Which one is easier? I don't know. I'm gonna say this one is more difficult, because if we did not use that trick that this is a quarter of a circle, we will have to use x equal to a sine of theta and then go through all of that. So because of that, I'm going to say this one was a little easier, though here we had to use a trigonometric identity to get to this point, and then we can realize, well, there's another little trick here. Well, this is 2 full cycles. Every time you have a full cycle of sine or cosine and we're integrating that and only that, we're going to end up with 0. So which one is easier? And the other thing is that we had to know more. We had to know more how to put this together. But then on the other hand, here we had to solve. So there's pros and cons on each one of them. Here I did not show step by step how to solve for y, and we get these complications here. Now, the one thing I wanted to point out, which is very, very important, when we are doing double integrals and things are pretty even, pretty symmetric, yes, we can do a double integral and multiply by 4. So multiplying by 4 here is okay. Multiplying by 4 may work here, but that would be purely coincidental. Yeah, I think it does work, but it's not so straightforward. So one thing is, watch out. Okay. We cannot split boundaries as we split regions. And this is what I mean by that. If we were going to go and do, oh, well, I'm just going to do a quarter, which did make sense when we did the double integral. Well, if we're using Green's theorem, then we have this portion from 0 to 2 pi of this r, but then we also have this, which we can call C1 going down, and then this that has to be added, which would be C2. So if we split into 4, yes, we may. However, it's not as easy as just going from 0 to pi over 2. We have to include C1 and C2. And you may be thinking, wait a minute, if I go from 0 to pi over 2 and multiply by 4, I am going to end up with the same answer. Yeah, I believe we do end up with the same answer. So does it really matter to have C1 and C2? In general, it does matter. If it doesn't here, it's because we're lucky. Because on C1, the equation that we need to have is that x has to be 0 on C1. And here, y has to be 0 on C2. And what are we integrating? We're integrating x dy. So when x is 0, this integral becomes 0. It should be included initially if we want to split, but the x is 0 on this boundary, so that saves us in the sense that we're not adding anything, we're adding 0. On C2, y is 0. Y is 0, and so the differential is also going to be 0. When either the integrand or the differential are fixed, then the integral is going to be 0. So it is coincidental that we get AB pi if we restrict ourselves to 0 to pi over 2 and multiply by 4. In reality, what we have to do is add those boundaries. So going from 0 to pi over 2 here without adding those boundaries would be incorrect. We're just locking in this problem if you were going to do that. What I'm trying to say is this. If you were doing this, going from 0 to pi over 2, and then multiply by 4 without making any note about those additional boundaries, then I have to take points off on your quiz or a test or any assessment because those have to be included. You have to make a point of saying maybe a side note that says, well, on C1 and C2, we're going to end up with 0 in this specific case. Now, for other functions, that might not be the case, so we have to take that into account. So when we are splitting regions, the boundaries have to be taken into account. Or the other way, this is a loose way to say it. The other way to say it is that the boundaries have to be taken into account. All right, let's start a second example. Example 2. Okay, we want to evaluate the double integral of, now we're not going to have 1, we're going to have x squared plus y squared with respect to the area over D, where D is the unit circle. So center at the origin, radius 1. Okay. So method 1. Without Green's theorem. We want to really practice both ways and compare the two. Okay, so the double integral of x squared plus y squared with respect to the area over the unit circle will be the integral of the integral. Okay, so the unit circle from -1 to 1. On the axis, on the y's, we're going to go from negative square root of 1 minus x squared to positive square root of 1 minus x squared. And then we're going to have x squared plus y squared dy dx. Okay, so that is the initial setup. We're familiar with the unit circle and how to set things up. Now, this function is totally positive. There's no negatives. And it is even with respect to those two and with respect to those two. Maybe it does help to understand what we're doing with this, what we're finding geometrically. So we realize that this is a paraboloid. You know, if you have z equals x squared plus y squared, we got a regular paraboloid. And then down here, we can have the unit circle. Yep. So what we are doing is finding the volume, because that's the region we're integrating over, and this would be the surface. So we're finding the volume underneath the paraboloid, but above the unit circle. So there's a solid. I guess the solid is going to look like this, like a cylinder on the outside, but on the inside, we are finding this. We're carving a paraboloid in this cylinder, and we're finding the volume of this solid after we carved the paraboloid into this solid cylinder. So that's what we're doing. And here we have the x-axis, the y-axis, the z-axis goes down there. So if we find the volume going from this to this region, just a quarter of it above this, it is because of the nice symmetry of this paraboloid. If we find again the volume above this quarter, then we can just multiply by 4 to obtain the whole volume. So I'm going to take advantage of the symmetry of what we're doing and integrate from 0 to 1. I forgot to put the 4. We can put the 4 inside. From 0 to the square root of 1 minus x squared. Let's put the 4 now because we're going to multiply by 4. X squared plus y squared dy dx. Okay, now I'm going to put the 4 outside because I had forgotten to put it outside, but it is a constant. Constants have a free passport that is very, very universal. They can go in and out whenever they want to. There are some places they cannot get out of, like square roots. They have to pay some kind of a price, but anyway, so we're integrating with respect to y. That means that this is going to be x squared y, and we're going to plug in that and that. So we're going to end up with x squared, plug in that, square root of 1 minus x squared, plus, and then integrating with respect to y means we're going to do y cubed over 3, and we're going to plug in the top and the bottom. So we're going to have the square root of 1 minus x squared cubed over 3, close parenthesis, with respect to x. All right. I'm going to do those integrals on the side. So we're going to do some side work. Some side work. Okay, so we want to do the integral. We're going to figure out the integral from 0 to 1 of x squared root 1 minus x squared with respect to x. So we're going to take and figure this out, only this part, and then we're going to do this one. So x squared square root 1 minus x squared dx. We cannot use, of course, the circle, we got a quarter of a circle or anything like that, because as soon as we multiply by x squared, this is distorted. This is not a circle anymore. Just the square root of 1 minus x squared, yeah, it would be a circle, but when we multiply by x, we don't end up with a circle anymore. And we cannot use a u substitution of 1 minus x squared because we need an x. We have an x squared instead. That creates a problem. Let's just use our trigonometric substitution. So we're going to say x equals sine of theta, and dx, of course, is cosine of theta d theta. And then we're just going to take it from there. So we're integrating from 0 to pi over 2 because that causes the x to become 1, which is what we want. Now we're integrating with respect to theta, so that's why we go from 0 to pi over 2 instead. So we're going to have sine squared theta. That is going to be cosine because 1 minus sine squared is cosine squared root of that cosine theta. And then dx is another cosine with the d theta. Okay. So we have sine cosine quantity squared. And all of us know that sine cosine is really sine of 2 theta, in this case over 2, but then we still have to square that from 0 to pi over 2. Okay, so that causes a 4 to factor out. Oh, 1 over 4, not just 4, but 1 over 4. Okay, so 1 over 4. That comes from the denominator, and then we're integrating sine squared. 0 pi over 2. But sine squared, because we're going to square the sine, is really 1 minus cosine double the angle. Now, this angle is 2 theta to start with. So when we double that, we're going to end up with 4 theta over 2. This 2 is new because that came from the sine squared. We already did the 2 in the denominator, square it, that became a 4, and we factor that out. Okay, so cosine of 4 theta, by the time we get to pi over 2, we're going to complete a whole cycle because pi over 2 times 4 is 2 pi, so we're going to end up integrating a whole cycle of cosine by the time we go to pi over 2 from 0. So that is going to give us 0 when we integrate. And so I'm not saying that this is 0. Maybe that's misleading. Eventually it will be 0 after we integrate because we're doing a full cycle of cosine. So we end up with 1/2 times pi over 2. Don't forget the 1/4. 1/4 times 1/2 times pi over 2. And that gives us pi over 16. Okay, so remember we are doing this integral. So we have 4 parentheses pi over 16 that came from this integral. Now we got to do that. I'm not going to do the integral of, I'm not going to include the 3 right now. Let's keep it here, plus 1/3. And let's just do this integral. Okay, so that's done. So we have a new problem, the integral from 0 to 1 of the square root of 1 minus x squared cubed dx. So this is a new problem. All right, we're going to use the same substitution because we have 1 minus x squared under the root, and that helped us out here. So now 1 minus sine squared is cosine squared. Take the square root, that's cosine, but then we're going to cube it. Cosine cubed theta, but then dx is another cosine, cosine theta. So we have cosine to the 4 d theta from 0 to pi over 2 under the same. So even though this is a new integral, different than this one we did here, we're going to apply the same substitution. So we got cosine to the 4, which we can split into cosine squared. And one of those two cosine squareds, so let me write this down as I do it, cosine squared theta, d theta from 0 to pi over 2. One of those cosine squareds may be written as 1 minus sine squared. So we got cosine squared theta, quantity 1 minus sine squared theta, d theta from 0 to pi over 2. And then we can split that into two integrals, the integral of cosine squared. Yep, cosine squared theta d theta from 0 to pi over 2 minus the integral cosine squared theta sine squared theta d theta from 0 to pi over 2. Now, this integral may be rewritten as 1 plus cosine of 2 theta over 2 d theta. So we're using that trigonometric identity minus, okay, sine squared, cosine squared, that rings a bell. Sine squared, cosine squared from 0 to pi over 2. That integral is exactly the same as this, which is equal to that, which is equal to this, which is equal to pi over 16. So there's no need to redo that, especially when we just did the work on the same page, minus pi over 16. Okay. Cosine of 2 theta, by the time we get to pi over 2, cosine starts at 0 at the top, and then it goes down. And by the time we get to, let's say, pi over 2 times 2 is just pi, we're going to end up at the bottom. So cosine starts at the top, we go all the way to the bottom. So we get a positive region and a negative region of cosine that are of the same magnitude. So they're going to cancel off, and we're going to end up with 0. So this contributes 0 to our integration. So we're really just integrating 1/2 from 0 to pi over 2. So that is 1/2 of pi over 2 minus this pi over 16. So that is 4 in the denominator, and that is just a problem of fractions. So we got 4 pi over 16 minus pi over 16, and that gives us 3 pi over 16. All right, this is side work, 3 pi over 16. That's what goes here. Remember, 1/3 came from that 3 out times, I forgot, 3 pi over 16. There it is. 3 pi over 16, close parenthesis. The 3 is simplified, so we got pi over 16 plus the 3 simplified pi over 16. Pi over 16 plus pi over 16 is pi over 8. So the final answer is pi over 2. Okay, so the volume of this solid, the whole thing above the unit circle under the paraboloid, is exactly, no more, no less than pi over 2. And we had to come up with some additional work. We started out here. This is without Green's theorem. We went through all of this, actually through here. We paused so we can figure this out on the side. We figured that out on the side. We plug in, and finally we get to pi over 2. Yeah, after doing this work. Well, method 2. With Green's theorem. It's good to do problems without the theorem and with the theorem so that we can compare, we reinforce what we do. It is better all around. Okay, so we're trying to find the double integral of x squared plus y squared with respect to the area over the unit circle. Green's theorem says, that's gotta be the line integral of p dx plus q dy over the circumference. But we don't know what p or q should be. Okay, so and remember, using Green's theorem assumes that this whole thing is the partial of q with respect to x minus the partial of y, of p rather, p, with respect to y. Okay, so I need to find a p and a q that give us this. And there are many possibilities for p and q. P, q, okay, let's make a table. So one possibility is I could just set q, I could set p to be 0. There we go. So that q carries all the weight. So when we do the partial of q with respect to x, we get this all at once. Yeah. So how do we go about it? I was looking at this table and I was thinking, we don't need the right side. Let me, sorry to do this. I'm just gonna put PQ because I wanna have more space. So we can have P equal to 0 and Q be responsible for x squared plus y squared. So if the partial of Q with respect to x gives us x squared to y squared, if I wanna find Q, all I have to do is do the antiderivative. So the antiderivative of x squared is x cubed over 3. The antiderivative of y squared with respect to x is xy squared. So plus xy squared. So if we just set q to be this and p equal to 0, we can apply Green's theorem and it will work. Or we can let p do the whole work and q be 0. So we can put 0 for q and then p be the one that creates those two. except that there's an extra negative. So we have to add an extra negative when we come up with the antiderivative. So the antiderivative of this with respect to y will be x squared y negative x squared y minus y cubed over 3. So those are the two components, p, q, p, q. Remember, back here when we were doing when I was in the very, very first page, when we were looking at antiderivatives, there are many antiderivatives, many antigradients. Here it gets even more complicated because there's not only many PQ, but there's PQ combinations. There are many, not only many P's and many Q's perhaps, but many P and Q combinations that will work. So this gets even more complicated. And somebody could say, wait a minute, why don't we do x cubed over 3, x cubed, oh, that should be here, x cubed over 3, and negative y cubed over 3. Let's see, let me double check. So the derivative of p with respect to x is going to give us x squared, and then minus derivative of this this one with respect to y, because there's another negative here, we're going to end up with plus y squared. So this would work, and there's probably many more. We gotta pick one. Okay, let's pause for a moment and talk about the boundary. So the unit circle, yep, goes this way, and I want to know a boundary for this, an equation for the boundary, and it is well known that r, which is a function of t, will, if we set x to be cosine of t and y to be sine of t, that will do, as t runs from 0 to 2 pi. Okay, so now we gotta choose. I don't really want to do 2. I want to end up with just 1, and this has negatives. I'm just gonna use this guy. So this one seems, even though there are 2 parts to it, this seems a little easier, I think. So we're gonna choose this guy. If you choose any of the other 2, you will end up with the right answer, unless I'm wrong. No, I think you will end up with the right answer. So there's a lot of stuff here. Let's set it up. So we got the double integral over the region of x squared plus y squared with respect to the area. That's equal to, again, I'm going to choose this guy. So that means that p is 0. This portion of Green's theorem is going to end up being 0. So we're just going to integrate q, which is this, with respect to y. So we're going to integrate over the curve x cubed over 3 plus xy squared with respect to y. Okay, the curve is given by this, and this is of course x, and that is y. So we have the integral from 0 to 2 pi of cosine cubed t over 3, that's the x, plus cosine t x sine squared t, that's y, times dy. If this is y, dy would be cosine t dt. Hmm. Hmm. I don't think we are going to save ourselves too much time, because this is the integral from 0 to 2 pi of cosine to the 4 of t over 3 plus sine squared of t cosine squared of t dt. So I'm distributing the cosine into those two. Those integrals are familiar. The sine squared, cosine squared was the side work we did for the previous problem. Well, it was part of it. We did not start with that. We started with this, and that was a side um, shot of this problem. Oh, but wait a minute, this is from 0 to pi over 2, and this is from 0 to 2 pi. As it turns out, for this particular case, well, we can probably just adjust. This is still going to be 0. We can just adjust this and put a 2 pi here, because everything else is going to be the same, except that we got to put a 2 pi here instead of pi over 2. So we need to multiply this by 4, and that gives us pi over 4. So this guy is pi over 4. The second integral is pi over 4. The first one also looks familiar. It was here, cosine to the 4. Cosine to the 4 is this. Boy, we have to make some adjustments to that. If we carry things over, and we gotta be careful, if we trace this, we will end up with pi over 4. But then the reason why we got that is because we place here a pi over 2. But the integral that we have at hand is 2 pi, close to 2 pi. So here we plug in 2 pi divided by 2, and that's going to give us pi. But then we subtracted pi over 16 from here, but that is really when we go to 2 pi, pi over 4. Boy. I think there is something wrong with this. I'm going to pause just to check where the mistake is. I just noticed where the mistake is. When we did the computation for that, I forgot to divide by 3. So here we need to divide this by 3. Okay, so pi minus pi over 4 is 3 pi over 4. But then we need to keep the 3 also there. So that simplifies, plus pi over 4. And that gives us pi over 4 plus pi over 4, which is pi over 2, which is exactly the same answer we obtained in the previous method without using Green's theorem. We obtained pi over 2. Now, which one is easier is not so straightforward, because I did not do those two integrations as part of the side work. I piggybacked on the side work we did for the method number 1. So something I want to establish is that this theorem, this Green's theorem, doesn't say that one is going to be easier than the other. We don't know which method will be easier than the other, whether we use a double integral or the line integral over the boundary, as opposed to the double integral over the region. things vary from problem to problem. It isn't true that one way is going to be easier always. Something I wanted to point out before we move on to another example is, you know, this is a solid of revolution. And in calculus 2, we learn how to figure the volume of solids of revolution. So let's include method 3. Okay, so how do we generate this solid? If you have the x, y, now this is I'm not going to set it up exactly the same way as it is here because we got x, y, and z. Um, so this is a different kind of setup. And we got a parabola, just y equals x. Y equals x. And we rotate this region around the y-axis. We can generate the same solid that is produced up here. And you remember from calculus 2, if we use the method of shells, so we take this strip, delta x, so we're going to integrate with respect to x, and then the height of this is, oh, I missed the x squared here, y equals x squared. So the y value is going to be x squared, so we're going to be integrating x squared. And then the radius here is another x. But then we need to multiply by 2 pi because we're going around, rotating around the y-axis, so 2 pi. And so we're integrating this. As x goes from 0, you know, we're adding shells, 0 to 1. So there we have it. So this is from Calc 2. So this is really x cubed, which is going to give us the antiderivative of x cubed is x to the 4 over 4. So keep the 2 pi. X to the 4 over 4, as we go from 0 to 1, is 1, 4. So there's the answer, pi over 2, same answer we got before without so much drama, which goes to show, you know, if there's a simpler way to do this, and shells, you know, we remember in Calc 2 how shells was so difficult. Actually, shells is the easy way to go. I mean, compare that with this method 1 without, and I'm not showing the work that was involved in figuring this out. There was another extra sheet to figure out those two integrals. And even with Green's theorem, it didn't get any easier with Green's theorem. We still have to do some complicated integrals. And shells, which we did in Calc 2, will get the answer in just 2 punches. Very, very easy. So that goes to show the simpler the method, and believe it or not, shells is way simpler than Green's theorem, whether we use double integrals or line integrals. Yep. So this was my other page. Example 3. Okay. So now we want to find the double integral of x squared plus y squared with respect to the area. So it's we can consider this as a volume over d, but d is going to be different. D is going to be the square from -1 to 1 on the y's, from -1 to 1 on the x's, and then the parabola is going to be sitting on top of this. So let me draw another picture. So D is this guy. I'm going to draw a couple pictures of D. So on the x, y plane, a top view, D is going to be this, from -1 to 1, from -1 to 1 on the y's. That's going to be D. So what are we obtaining? It will be, so there is the paraboloid. So one corner is going to be here. So we're going to have this kind of shape. And then we're going to find, boy, there. We're going to find the volume of the solid that is above the square, then from -1 to 1 on the x and on the y's, and below the paraboloid. So we're not going to have a nice solid circle on the top of the solid. Yeah, the solid is gonna, I'm gonna attempt to draw it here. It's gonna kind of be like this, and then it's gonna come back this way and this way. And that is the inside. Actually, the outside is a cylinder. So there's a cylinder to start with, carve a paraboloid inside, but in such a way that some parts of it go up and some parts are lower. That's the kind of solid we will obtain, which is gonna, and the area, the volume of that solid will be more than pi over 2, because if you just go around this way on the lowest point, that's gonna give you pi over 2. So we're including a little more of it in this. Whoa. So this is D from -1 to 1 on the x's and on the y's. And that's how we're gonna do it. So method 1, that is without Green's theorem. I'm going to put GT for Green's theorem. So without Green's theorem, okay, I'm going to use symmetry. This is totally positive, and it is symmetric with respect to the x and the y. So if you go on the negative axis, that's not going to affect this output. On the negative y's, nothing is going to be affected whether you go on the positive or negative. So the double integral of x squared plus y squared close with respect to the area over that region is going to be 4 times the double integral, again, because things are so even and positive that we can just go from 0 to 1, 0 to 1, instead of going from -1 to 1 and -1 to 1. X squared plus y squared dy dx. So 4 integral from 0 to 1. So integral of this with respect to y is just going to be x squared y. As y goes from 0 to 1, we just have x squared plus y cubic over 3, what y cubic over 3 from 0 to 1, 1/3 dx, 4 times x cubed over 3 from 0 to 1. That's going to give us 1/3, 1/3 x from 0 to 1, 1/3. So that's going to be 2/3. So 8/3. 8/3. Let me double check. 1/3 plus 1/3 is 2/3 times 4, 8/3. That seems high because that is 2 as a mixed number and 2/3. So it's about 2.67. That is the answer. This is the way we usually want to write the answer. But it is about 2.67. And that seems like a big increment on our volume from the previous problem. The previous problem was pi over 2, which is 1.57. I guess it isn't to 2. Oh boy, we added a whole unit. Okay, so notice that method 1, which is just the regular double integral, did not involve much of a drama. It was actually quite straightforward. Method 2. We can come back and double check that we got the right answer. Well, let's do it the other way, with Green's theorem. Okay, so instead of going over the, I'm going to use the same symmetry. I'm going to multiply by 4, and we're going to integrate over this square. I'm not going to have enough room here, so So let's start all over with method 2. Okay, which involves using Green's theorem. All right. So we're going to integrate over this square from -1 to 1. There is so much symmetry on the solid that might just as well integrate over this square, subsquare, which goes from 0 to 1, from 0 to 1 on the axis and the y. So this is the x-axis, this is the y-axis. And we're going to multiply it by 4. All right. So, but then what are we going to integrate? We want to find, remember, the p and the q, so that works here. We're not going to integrate this. We're going to integrate one of those. Let me integrate this guy, x cubed. So, okay, so first of all, the double integral of x squared plus y squared with respect to the area over d, and d is the entire thing, will be equal to 4 times, using Green's theorem, the line integral of, okay, so this is 0, and we may use any of those 3. I'm almost tempted to do this guy. Negative y cubed over 3. No, but let's do this one instead. X cubed over 3, x cubed over 3 plus xy squared, close parenthesis, with respect to y, by Green's theorem. Now, the reason for that is because we are choosing p to be 0 and q to be that. So this part of this should be part of your work, where you're actually showing what you're choosing for p and q, if you're doing this kind of problem. Now, C would be the entire boundary. The boundary has 4 edges. Don't neglect, don't think that we're just going to go the outer edges. We have the inside edges also. So now those follow different formulas. I'm going to draw a bigger picture. Yep. So there it is, the x-axis, the y-axis. And we're going to further split. We're going to start here. We're going to split this into C1, C2, C3, and coming back around C4. Remember, we have to go, in order to use Green's theorem, we have to go in counterclockwise direction. What defines C1 will be that y is equal to 0. What defines C2 is that x is equal to 1. What defines C3 is that y is equal to 1. And what defines C4 is that x is equal to 0. Okay. While y goes from 0, rather, as x goes from 0 to 1, in this case, y goes from 0 to 1. In this case, x goes from 1 to 0. And in this case, y goes from 1 to 0. Whoa. Okay, so the 4 stays. And this is going to be the integral over C1 of x cubed over 3 plus xy squared with respect to y, plus the integral over C2 of x cubed over 3 plus xy squared dy, plus the integral over C3 of x cubed over 3 plus xy squared dy, plus the integral over C4 of x cubed over 3 plus xy squared dy. Close the bracket because that has to be multiplied by 4, each one of them. All right. Now, when on C1, y is 0. Okay, so this guy is going to be 0 on C1, not on C2. Okay, who else is going to be 0? X is going to be 0 on C4. There's C4. So there's an X and there's an X. So the entire thing is going to be 0. The entire integral, because both terms contain X, but in that path, X is 0. So all of this is 0. Here, not all of it is 0. Oh, but Y is 0 in path 1. So the differential, I guess we didn't even have to put 0. The differential is going to be 0 anyway, because when you do dy, you're going to get 0. If y is 0, dy is 0. If y is constantly 0 across the axis, the whole thing is going to be 0. So that was 0 to start with. So those two integrals do not contribute any because they're going to end up being 0. Okay. We're lucky that we are on the x-axis and on the y-axis, because then one of the variables is going to be 0. But if this region was shifted off, not so that the x-axis nor the y-axis were in any part of the boundary, then that would not be true. But then again, dy, if y is 1, dy is going to be 0. Again, if y is 1, constantly 1 across the whole thing, then dy is going to be 0. There's no increment. So that's going to be 0. It looks like the only thing that is going to, so x here on C3, x is 1. Okay, so that's going to vanish. This entire integral is going to vanish. This is going to vanish because dy is 0. This is going to vanish because the x's are going to be 0. So the only one that survives is that one. That one is not going to be 0. Boy. Yeah, imagine if this was a triangle. Then the paths would be even more complicated because the diagonal adds complications. Anyway, so this is the only one that survives. 4, keep the 4. And we are going to integrate, this is C3. So this is C1, C2, C3 from, x is 1. Getting myself a little confused here for a moment. This is 1, 2, 3. X is 1 on here, but y changes. Sorry, I did not mean this to be 0. This is the one that is 0, because y is 1 and dy is 0. So that one is the one that is 0. This one is the one that survives. So 0, 0, 0, second one survives. All right. So x is 1 here. So that means we have 1/3 plus x is 1. So we have y squared dy as y goes from 0 to 1. So that is 4. 1/3 y from 0 to 1 is 1/3 plus y cubed over 3, 1/3. So that is 2/3 times 4 is 8/3. So either way, we end up with the same answer as we did before. Whoa. So notice that if we want to find the double integral, oh, this was not the one. I'm looking for my example 3. Oh, there it is. Example 3. Yeah, originally. Notice how easy it was to do the example without using Green's theorem, without going to the boundary. straightforwardly, you know, 2-3 punches, boom, we got the answer, 8/3. If we go over the boundary, things get more complicated. And we got zeros. We cut some work by having zeros. Had we stayed with the original boundary, because we multiplied by 4, we were able to do that because things are very, very uniform, and we are familiar, excuse me, with x squared plus y squared, which is a nice, a very, very nice paraboloid. And we know the paraboloid will be symmetric around. So had we gone through -1 and -1s and so forth, then things would be more like, all the integrals would be like this one, where we have to fix one of the x or the y's to 1 or -1. Actually, that is not entirely true, because 2 of them will have a, anyway, it's not a bad idea to, instead of multiplying by 4 and going around this way, just go all the way around and use those paths. Do practice going through different paths on the integrals. In this case, using Green's theorem to convert a double integral into a line integral, in my opinion, is way more work than had we just stayed with not using the Green's theorem and just find the double integral, and that's it. So in this example, yeah, it is way easier to use Green's theorem the other way. So if you were given this kind of a problem, it is way easier to go back to this double integral as it's shown here. So the bottom line is, when you're using Green's theorem, we do not know necessarily in advance which one of the two sides of the Green's theorem is going to be easier. The double integral could be easier than the line integral, or vice versa. Maybe the line integral is easier, or maybe they're about the same amount of work as we did in one of the examples. And to finish this up, I just want to say that the previous example we could have done very, very quickly using the method of shells to find the volume of the solid, because the solid was a solid of revolution. This solid, you know, the solid that we have here kind of looks like this. And actually, it's just the bottom of it. Yeah, so there's, oh, not even, it doesn't close on a nice top. The top actually goes down and up and down and up. So it's kind of like a crown. Yeah, it's kind of like, yeah, something like this, perhaps. Kind of like a crown that is, and then it is, yeah, more like this. So this is what we found. And it has a carving inside that has the shape of a paraboloid. This is not a solid of revolution. It doesn't matter what region you take and you revolve it. You're not going to get this solid because of this going down. This edge goes down and up. So we cannot do this. We cannot do this problem with, I would call it calc 2 means, as we did in the previous example. So not everything can be simplified. We do need double integrals. We do need line integrals. And sometimes Green's theorem can help us a lot and shorten our work. And with this, we'll stop this video.